Hello, good morning, and welcome to Wolfram Technology Conference. So this session is titled Zeta Functions from Riemann to Feynman, and here we will present, together with my colleague Jayanta, will present the recent developments in this topic. And so the zeta functions, together with harmonic numbers and polylogarithms, are the native language of many difficult problems, from some summations in number theory and combinatorics to differential equation methods for multiscale Feynman integrals and others. And we, in this talk, will introduce a coherent family of symbols: alternating harmonic number, hyperharmonic number, multiple harmonic number, MultipleZeta, HarmonicPolyLog, MultiplePolyLog, and generalized polylog functions with some features and deep integration with other functions like sum, RSolve, integrate, DSolve, and others in the system. And we will start from a historical overview of harmonic numbers, and then we'll shift to the zeta functions and polylogs. So let's start. So generally speaking, harmonic numbers are a bridge between discrete sums and analytic functions, and the classical definition is presented here. So the harmonic number is a sum of the reciprocal of the first natural numbers. And we can evaluate this sum directly and get the harmonic number, or we can generate, say, 10 first harmonic numbers. And also, the harmonic number, alongside with this definition, can be defined via this integral. And okay, for real number n's, in fact for integers, and also the harmonic number satisfies different recurrence identities, one of which is presented here. So it's connecting the harmonic number of order n with the harmonic number of order n plus 1, and it's quite understandable formula. Also, there is a lot of functionality connected with harmonic numbers, say the generating function, written as a logarithm. And in general, this harmonic number appears in several applications, from number theory, special functions theory, and a lot of other tasks. Two examples are presented here, like the limit of harmonic number, which is Euler's gamma constant, or say the polygamma of order 0, which is nothing else than the digamma function, which can be written in terms of harmonic numbers. The point is that this definition of harmonic number can be generalized, and let's talk about that. So the harmonic number is given by this sum, and it can be generalized to the following form, which is called the harmonic number of order R, and divided by this sum. And obviously, when this R is 1, we get the ordinary harmonic numbers. Also, we can even go further and define a harmonic number of order R and decoration value of S, which is more advanced sum. And here, when this decoration value S is 1, then we are getting the harmonic number of order 1. So this is some generalization of the original harmonic numbers, and we have implemented them in the system. We can see, say, harmonic number of 4 is this. Harmonic number of 4 of order R is this sum, and the order R, the decoration value S, is this one. And here is the complex plot of 2-argument harmonic number, while the ring plot of harmonic number with 3 arguments is this one. And this is a new function, the 3-argument harmonic number. And yeah, of course, some couple of sums just showing this. So this sum is a harmonic number, 3 arguments, and also we are able to calculate some sums having harmonic numbers inside. The next development of harmonic numbers is called the alternating harmonic numbers. And if the harmonic numbers are defined like this, then the alternating harmonic numbers are the same sums, but here we have -1 power k plus 1. So these are also new functions in the system. And let's compare the harmonic number and the alternating harmonic number. So these are first 10 harmonic numbers and first 10 alternating harmonic numbers. And the plot of this one. So here the blue line is the harmonic number, and the orange one, is the real are the real and imaginary parts of the alternating harmonic numbers. Yeah, some comparison. And also the alternating harmonic number satisfies different formulas like this one. So this is a recurrence relation connecting the alternating harmonic number of order n with n plus 1. And yeah, of course, the defining sum. The next step connected with harmonic numbers are the hyperharmonic numbers. And these are calculated recursively using this formula. And here we have a parameter which is called P, which is the level of this hyperharmonic number. And this hyperharmonic number of level P is calculated recursively using this sum. And here we have to give some initial values. And the hyperharmonic number of level 0 is 1 over n, and hyperharmonic number of level 1 is just the harmonic number. And we can see this, like evaluating the harmonic number and evaluating the hyperharmonic number. And the plot of hyperharmonic number. Yeah, also the hyperharmonic numbers that are new in the system, they satisfy this recurrence relation, which can be checked. And the point is that these hyperharmonic numbers of level P can be also generalized. We have two generalizations. The first one is called hyperharmonic number of level P with weight R, and hyperharmonic number of level P with weight R and decoration value of S. They are also calculated recursively, and they are, say, somehow involving the harmonic number of order R, and the harmonic number of order R with decoration value S. So if we could try to sum the harmonic number with this decoration value, then now in the system we will get the hyperharmonic number. And the important point here is that harmonic numbers are generally initially, say, defined for integer numbers, but we can analytically continuate these functions using different special functions like the di-gamma function, zeta function, large phi function, polylog function, and others. So all this information is available in the system. If we will apply function expand to this, so the harmonic numbers analytic continuation is written in polygamma functions and so on. For alternating harmonic number, we also have analytic continuations written in zeta functions, large phi, and for hyperharmonic functions, we have here polygammas. So this was like, there are some new functions, the harmonic number of 3 arguments, the alternating harmonic numbers, and hyperharmonic numbers, and also another generalization of harmonic numbers is multiple harmonic numbers, which is, say, generalization of harmonic numbers when we have, say, different orders R. The multiple harmonic number is written like this sum. So here the n is order user given, it's the number, and R's are the orders. We can evaluate this multiple harmonic number and compare with the output of n sum directly from its definition. When we have only one R, then the multiple harmonic number is obviously the harmonic number, and yeah, table giving some multiple harmonic numbers. And the important point here is that the harmonic numbers and their generalizations are written as finite sums. But what if n goes to infinity? The point is that these cases are nothing else than the zeta functions. Say the harmonic number when n is infinity and order is 4 is the zeta 4. Alternating harmonic number is given also the zeta functions, And the multiple harmonic number when n is infinity is nothing else than the multiple zeta, which will be presented in the next slide by my colleague Jayanta. So Jayanta, please.
So this is the series representation of the two-argument harmonic number, as you can see, and Tigran presented it. And as Tigran said, when n goes to infinity here, we get zeta. So harmonic number infinity comma something that becomes zeta. And if we extend it to multiple indices, then we get multiple zeta. So these exponents over here are coming in the list here in this argument. So that is our multiple zeta. And multiple zeta is actually a multiple harmonic number at n equal to infinity. So similar to this one-dimensional case, as you can see. Now for simple arguments, multiple zeta will auto-evaluate in terms of zeta and so on. But if these parameters are relatively large, it may not auto-evaluate to simpler functions, but we should be able to numerically evaluate this. Now, this is the integral definition of zeta. So, and these are known as iterated integrals. So, here, as you can see, these iterators form a particular pattern. So, x5 goes from 0 to x4, x4 goes from 0 to x3, and so on. And finally, x1 goes from 0 to 1. And there are 4 poles of magnitude 0 and 1 pole of 1 magnitude. So, that's how we get zeta 5. Now here, if we add more of 1 minus x type of terms, we get multiple zeta. So the 5 here is coming from this part and 3 is coming from this part. And this has different applications. I'll talk about these little later. Now let us look at the next special function, multiple polylog. So this is the series definition for the 3-argument harmonic number as Tigran had presented. So if we take n to infinity, we get polylog. And yeah, this is the identity as you can see. So when we set n equal to infinity, we get polylog. And if we extend the same thing to multiple indices, then we get multiple polylog. So these are the exponents here from the denominator, and these are from the numerator. Okay, and this is actually a decorated multiple harmonic number at n equal to infinity. So by decorated, I mean that we have these decoration values present over here. So we can compare this with the one-dimensional version here. Now again, similar to multiple zeta, multiple polylog will auto-evaluate in terms of log, polylog, and so on for relatively simpler arguments, or if the arguments follow some special patterns. But otherwise, in general case, it may not auto-evaluate, but we should be able to evaluate it numerically. Okay, so these are the last two special functions in this category, harmonic polylog and generalized polylog. So we saw that if we generalize the series definition of polylog, we get multiple polylog. And we'll see that if we generalize the integral definition of polylog, we get harmonic polylog and generalized polylog. So this is the integral definition of polylog. So basically this 5 here means that we have 4 poles of magnitude 0 followed by 1 pole of magnitude 1. And the second argument comes here as the upper limit. Now, this is the integral definition for the 3-argument polylog, which is the Nielsen polylog. So here what happens is that the first argument that gives rise to patterns like this, and then here 2 means that we will have 2 poles of magnitude 1 in this fashion. So that's how we get 3-argument polylog. Now, if we generalize this to arbitrary poles from the set -1, 0, and 1, not just 0 and 1, and with this specific pattern, we get harmonic polylog. So here is an example. So here we have poles of magnitude 0, then -1, 1, 0, and 1. And this is actually same as this one. Basically, the poles, as you can see, are contained here. And this is an abbreviated notation that we use, but actually the poles get straight translated into a list like this in harmonic polylog. So that's the harmonic polylog. And if we further generalize this to arbitrary complex numbers, so that means the poles can be any real or complex numbers, then what we get is the generalized polylog or Goncharov polylog. So as you can see, these are arbitrary complex numbers and we get generalized polylog here. So the hierarchy is that we have log, then 2-argument polylog, then 3-argument polylog, then harmonic polylog, and then finally generalized polylog. And as you can see here, generalized polylog can represent all of these: log, polylog, 2-argument, 3 arguments, and harmonic polylog. Now, similar to the other functions, harmonic polylog and generalized polylog will auto-evaluate for certain simple parameters. Uh, so here, basically, yeah, so if the endpoint is 1 and if these poles are only 0 and 1, then it will auto-evaluate to multiple zeta. But otherwise, in general case, it may not auto-evaluate to simpler functions, but we should be able to evaluate those numerically. Okay, so let us look at some applications. So basically, there are two main categories of applications: series-related applications. That means sum, RSolve, generating function, and so on. And these are the functions used. And then we have the integral related applications, basically in integrate, DSolve, asymptotic DSolve, and so on. So in some or series related applications, the notable one is what is called an Euler sum. So it is basically a sum of harmonic numbers. So the general Euler sum is written as something like this. So we have n as the sum index. So we have n to the power of something, something to the power of n, and then we have some harmonic number to the power of p1, some other harmonic number to the power of p2, and so on. So these h can be any harmonic numbers like harmonic number, alternating harmonic number, hyperharmonic number, multiple harmonic number, and so on. So let us look at some examples. So for example, here, as you can see, we have harmonic number and alternating harmonic number, and it is a finite sum. So we get answers in terms of multiple harmonic number. And usually these are pretty fast unless the exponents are large and so on. Okay, so here we have two harmonic numbers. One is the regular one and another is the 2-argument harmonic number. So this is an infinite sum. We get answer in terms of multiple zeta. Here we have harmonic number and multiple harmonic number. We get answer in terms of multiple polylog and so on. Okay, so certain solvers such as RSolve, generating function, and so on, they use this Euler sum machinery in the background. So those like for these did not evaluate in version 14.3. So those will start evaluating. And let us look at some integral related applications. So the main one is what is called the iterated integrals. And now we are able to compute this type of rational iterated integrals. This means these are all rational functions of x1, x2, and so on. And the iterators have some specific pattern, as you can see. So, and it can be shown that like except in the degenerate cases, this can be written as a sum of generalized polylogs. And of course, the generalized polylogs may auto-evaluate to some other functions like harmonic polylog, polylog, log, multiple zeta, and so on. So let us look at some examples. So these we had already seen. So as you can see, this is a rational iterated integral that evaluates in terms of multiple zeta. And these are pretty fast now. In 14.3, these would either return unevaluated or these will be very slow sometimes, would return huge answers and so on. So this gives us polylog, then harmonic polylog, generalized polylog. Yeah, for example, this one, as you can see, this does not fit into any definition, but this is a rational iterated integral, and we get answered in terms of generalized polylog. And as you can see, it is very fast. Okay, so let us look at another application, an ODE system. So consider this linear first order ODE system of this type. It is a perturbative ODE system where we have a perturbation parameter. So we call it a rational ODE system if all the elements of mx are rational functions of x, and if we call it a Fuchsian ODE system if the elements are rational function of x with no polynomial part and all poles are of multiplicity 1. So Fuchsian ODE system is a subset of rational ODE system. But this is important because this appears in Feynman integrals. So here is an example. So as you can see, this M matrix, all these are rational functions of x, and now we can solve this type of problem using asymptotic DSolve value. In 14.3, I think, yeah, it returns a huge answer after some time, and it contains unevaluated integrals. But now, as you can see, we will have the answers in terms of generalized polylog. So to show the relationship with Feynman integrals, basically there is a method called differential equation method for solving Feynman integrals, and it has some steps. So the step one is that we reduce the integral to a set of master integrals using integration by parts, and there are some external packages for this. And those master integrals actually constitute a rational or a Fuchsian perturbative ODE system. Now in step 2, we reduce that system to a Fuchsian perturbative ODE system in epsilon form. So epsilon form means that we can fully take out the epsilon from the matrix. And then in step 3, we solve it. So we can use, for example, the package find calc. And yeah, so in the step 2, this reduction can be done using packages such as Libra or Fuchsia. Now, as you can understand, we will natively support step 3 in Mathematica. So we should be able to find this perturbative solution directly. And we support to some extent step 2 as of now, because as long as it is in epsilon form, we can solve those rational ODE systems. Okay, so that's all more or less. I'll conclude with some remarks that, yeah, as Tigran said, that we introduced some new harmonic numbers. So we had harmonic number n, comma r. Now we introduced harmonic number n, comma r, comma s, and we introduced the alternating versions of these, alternating harmonic number n, comma r, r, comma s. Similarly, hyperharmonic number p, n, n, r, n, r, s, and similarly multiple harmonic number. And the applications are finite Euler sums, generating functions, etc. And we have some new zetas and polylogs now: multiple zeta, multiple polylog, harmonic polylog, generalized polylog. And the applications are Euler sums, iterated integrals, rational ODE system, and so on.